Hi everyone! This video will quickly review an aspect of radicals, which is rationalizing the denominator. Now the reason we have to rationalize the denominator is because, like in example 1, it's not mathematically proper to have a radical in the denominator of a fraction, or else the fraction is not considered totally simplified. So there's a few just foundational things to understand to help you understand why what we're going to do actually works. So first off, we know that anything over itself just has a value of 1. We also know that anything times 1 is just itself. So nothing changes. We're always allowed to multiply something by 1. And then lastly, in this example, the square root of 3 times the square root of 3 equals the square root of 9, which just simplifies to 3. So multiplying the square root of something by itself gets rid of the radical. So applying those things to rationalizing the denominator, in example 1, we have 3 over radical 2. In order to simplify this and rationalize the denominator, we would multiply that by radical 2 over radical 2, because we're literally just multiplying by 1, which doesn't change anything, and it's going to help us out. So when we multiply fractions, we multiply across, so 3 times radical 2 is just 3 radical 2, and radical 2 times radical 2 is just 2. So what we just did is we got rid of the radical in the denominator of our fraction, and this would be considered an appropriate answer. All right. You might find an example where you need to do one little extra step though, or multiple, depending on the problem. So in example 2, we're going to do the same exact thing. In order to rationalize the denominator, we multiply by root 3 over root 3, which again is just multiplying by 1, so we can do that. So then when we multiply, that ends up 12 root 3 over 3. But then you might notice that here we have a fraction that can be simplified a little bit further. So we know 12 over 3 is just 4. So our final answer to this would just be 4 root 3. And now it's totally simplified. You may have to use this concept when finding the side lengths of special right triangles. So just as an example, in a 45, 45, 90 triangle, we know that it's an isosceles right triangle, right, where we have the right angle. The legs both have the same length, they're the same, and then the hypotenuse is that leg length times the square root of 2. Sometimes you're going to be given an example where it only gives you the length of the hypotenuse. And if that happens, in order to get from the value of the hypotenuse to the leg, you're going to divide the hypotenuse by radical 2. So let's use this as an example. It says find the value of x. Now we know that this is the hypotenuse because the legs are both x. This is an isosceles right triangle. We see the right angle here. These angles we know are congruent, as well as the sides. So we're starting with the hypotenuse, and we need to find the leg length. Well, our rule says that we divide the hypotenuse by radical 2. So we divide 18 by radical 2, and this would actually be our side length. However, we have this radical in the denominator, which is not mathematically proper. So we rationalize that by doing just what we did earlier. Multiply that by root 2 over root 2, and we get 18 root 2 over 2. Then we simplify the 18 over 2 because we know that's 9. And our final answer just becomes 9 root 2. So the length of the legs of our hypotenuse are both 9 root 2. All right, great job.